we have so far covered three major types of power converters. We covered AC to DC, which is also called rectifier. We covered DC to AC, which is also called inverter. And then DC to DC. Another name is which we call chopper. Now, actually, chopper, this name is usually used for direct DC to DC. Okay, for isolated DC to DC, usually we probably do not call that chopper. And today we're going to talk about the last type, one of the four types, AC to AC. For AC to AC converters, we don't have a commonly used special name for that. We'll see that sometimes it's also called AC controllers. Sometimes it's called frequency converters. If the output AC power, AC energy, has the same frequency of AC energy from the input side, then we can usually call that AC controllers. This is what we usually call AC controllers. That's when the output AC energy frequency, AC voltage frequency is the same as the input AC. Then this type of AC to AC converters is also called AC controllers. Well, then you may ask, what can we change? What do we change? We change magnitude. That's very obvious. We can change magnitude of the AC energy. And if the output AC voltage or current has a variable frequency, the output frequency may not be the same as the input AC voltage frequency, then this is also called frequency converter. Frequency converter. And we have a special name. Frequency converter is also called cyclic converter. There is a special name for frequency converter. Cyclic converter. Okay, this is the basic classification for AC to AC converter, based on whether the output AC voltage has the same frequency of input or not. Okay? And then if you want to do further classification, for AC controllers, we can also do a classification one step further, based on different control methods. Okay, for AC controllers, we can do a further classification based on different control methods. And in general, there are four commonly used control methods for AC controllers. And probably we have seen some of them before. Let's see, the first one, phase control. Phase control. Another name is what we call delay angle control. Delay angle control. Okay. We have seen these control methods actually in AC to DC converters when we talk about rectifiers, thyristor rectifiers. In that chapter, we can control the output voltage of the thyristor AC to DC rectifier based on the controlling on the triggering delay angle alpha. Okay, that's called phase control, because we are controlling at what phase angle we send turning on signal to each of the thyristors in the circuit. And by changing this triggering delay angle, we can adjust the average output voltage. So that is exactly phase angle control or phase control or delay angle control. So we have seen this before. And actually the third one, PWM control. PWM is actually the acronym of this one, pulse width modulation. The third one, this is the first one, PWM. PWM control. We actually have seen this also in the previous chapters. The typical power converters we have seen that employing PWM control is actually DC to DC converters. If you still remember, for DC to DC converter, we always control duty cycle, right? By controlling duty cycle, we can adjust. For example, for buck converter, the average output voltage is always equal to duty cycle multiplied by the input voltage. Okay, so we can always control the average output voltage for DC to DC converter by adjusting duty cycle. And if you still remember, duty cycle is actually this thing. Duty cycle means for how much time, okay, in a controlling period. This is a controlling period. For how much time you set the power semiconductor switch under on state. For how much time you turn on the switch. And then duty cycle is defined as T on over T. And usually the controlling period is constant. We usually do not change that. And if you change T on, you change duty cycle. And when you change T on, this actually, if you look at this waveform, this can be let's see, if this is the gate signals for the power semiconductor switch. Okay. Then if you want to turn on the switch, you send the high level gate signal to the switch. If you want to turn it off, you send usually a zero level or even negative level of voltage signals on the gate. So by changing duty cycle, you are actually changing T on. When you are changing T on, this is actually T on is the width. This is the width of a pulse. Okay. So changing of duty cycle is actually changing of pulse width. So by changing pulse width, you are changing duty cycle, therefore you are changing the output. So that is actually a kind of pulse width modulation. So that's the third method. And actually for AC controllers, we have two other control methods. We didn't see that before. One is what we call integral cycle control. Okay, and the fourth one is on-off control. And when an AC controller is employing integral cycle control, we have also a very special name for that. It's also called AC power controller. We have a special name for integral cycle controlled AC controller, which is called AC power controller. Okay, when the AC controller is employing on-off control, the fourth one, we also have a special name for that, which is called electronic AC switch. Electronic AC switch. We will explain these different names later when we get into all these different control methods. But I just want to show you that we have this classification for AC controllers based on different control methods. For frequency converter, that means for the AC to AC converters that have different output frequency than the input, we also can do a further classification based on control methods. And for this type, we have usually used two different control methods. One is phase control, the other one is PWM control. And we do have a separate individual special name for these two types of controlled frequency converter or cyclic converter. If this cyclic converter is employing delay angle control or phase control, then this is called also thyristor cyclic converter, because this is usually applied to thyristor-based cyclic converters. And if this cyclic converter is employing PWM control, you just have a feeling of that. We are changing the width of a pulse, controlling pulse. Then that is also called matrix converter. This is a very special name. We never see that before. Matrix converter. Why is that called matrix? We'll mention that when we get into that in detail. Okay? And then cyclic converter, this name, in here we are using this as a different name for frequency converters. That means as different name for AC to AC converters that is providing variable output frequency output. Okay? But actually, sometimes this name, cyclic converter, is also used to refer to broader sense power converters. Okay? Sometimes it's called, for any ordinary AC to AC controller, we can also call that cyclic converter. No matter the output frequency is same as input or not. Some people use that as a general name for all the AC to AC converters. And sometimes some people use that for a narrow sense. In narrow sense, they use this name only for only for cyclic converter, only this part is called cyclic converter. So I just want you to notice this difference. Don't be confused by that. So let's get into all these different power converters in the following discussion. We'll talk about AC voltage controllers. So this is a special name when you are using, let's see, I forgot to mention that you have a special name when you are using integral cycle control, which is called AC power controller. When you are using on-off control, which is called electronic AC switch. But we do also have a name, special name for AC controllers under phase control and PWM control. Okay. For the first and third one, we also have a special name. For the first one, which is also called AC voltage controller. And for the third one, we are using the name AC chopper. That is similar to DC. When we are using PWM control for DC to DC converter, remember we call that DC chopper, and a special name. But in AC to AC controllers, when you are using PWM control, we also call that AC chopper. So just want to mention that. Phase control, which is also called VC voltage controller, PWM control, which is also called AC chopper. Okay. Some of you may have been confused already. Don't worry, we'll get into each of them individually. Let's look at this AC voltage controller first. That means we're now looking at the first one, the AC controller under phase control, which is called AC voltage controller. The first one AC voltage controller. We'll talk about single phase AC voltage controller and three phase one. Actually, this AC voltage controller, if you look at the single phase circuit, is very simple. Okay? If you look at this circuit diagram here, very simple circuit diagram. On the left-hand side, you have the AC input voltage source. On the right-hand side, you have the load. Okay? And of course, here we're looking at resistor load first, if the load is just a resistor. Then, other than the input and load, and what you have in the power converter is just a pair of thyristors. So very simple. This is even simpler than in the previous chapter when we talk about DC to DC converters. We mentioned that we have some basic DC to DC converters. We have buck, boost. Those are very simple. For buck converter, we need just one, let's say one fully controlled device, one diode, one inductor, usually. So we need three components between the input and output side. But here, actually, we need even smaller number of components than that. We need only a pair of thyristors. So very simple. And this pair of thyristors are connected, these two are connected in parallel and actually anti-parallel. In an anti-parallel way. I use the word, I'm not sure whether you still remember that. Anti-parallel. Anti-parallel way. Okay? And the operation principle is also very simple. We have AC voltage input here. Remember, we have a rule. We can always follow this rule when you start to analyze thyristor circuit. What is that rule? Start from diode circuit. Okay? You can always replace thyristors with diodes first and see how those diode circuits are working. And then you have better understanding and you start to analyze thyristor circuit. Because the diode circuit is always equivalent to the thyristor circuit under the triggering delay angle alpha equal to 0. Okay, that's always exactly equal to each other. So if you change this pair of thyristors to diodes, what does this circuit work? How does this circuit work? It will be just working like this is a short circuit. This pair of diodes are just short circuit or a always on switch. Okay, and all the input voltage will be always applied to the load, no matter the AC voltage input is positive or negative. This is always on. Okay. When this input voltage is positive for this part of time, the current will be flowing through VT1. This is a diode flowing through diode VT1, load, and back to the source. And if the input voltage is negative, this current will be flowing out from the lower side of the AC input through the load, and then through diode VT2 back to the upper terminal of AC input. So very simple. Okay, so that's exactly the same, equivalent to the thyristor circuits when you trigger VT1, VT2 at triggering delay angle alpha equal to 0. That means because for VT1 VT1 will be starting to conduct from this point. VT2 will be conducting starting from this point. So the triggering delay angle alpha will always be counting from this point and this point. For VT1, we will be counting from this point. For VT2, we'll be counting from this point. And that's what we have a special name for that, for those 2 points. What special name is that? The time instance when triggering delay angle alpha is 0. We have a special name for that. What is that? Natural commutation points, right? Natural commutation points. Okay, that's when triggering delay angle alpha is 0. Then, when I change alpha, let's say I do not trigger VT1 until after a certain time, counting from this natural commutation point. As this is alpha, let me use until here. This is alpha. Okay, when the input voltage is positive, I do not trigger it yet, okay? Until at this instant, when this phase angle comes to alpha, I trigger VT1. So before that, there will be no current flowing because these two pairs of thyristors are both blocking. No current flowing, therefore, there's no voltage on the load. So the output voltage here, you can see, will be exactly 0. When I trigger VT1 at this instant here, because VT1 now is under positive voltage, this input voltage is positive, applied to VT1. Therefore, when I trigger VT1, VT1 will be conducting. When VT1 is conducting, the current will be flowing through VT1 load. And therefore, load voltage UO will be exactly the same as input voltage U1. Exactly the same. Okay? Until when this input voltage has decreased to 0, and therefore, because this is a resistor load, the load current, okay, will also be decreased to 0. Same waveform as the load voltage. So when this is decreased to 0, then VT1 turn off. Remember, we cannot turn off thyristor through gate signals. Thyristor can only be turned off when the current flowing through the thyristor is decreased to 0. So at this instant, when the current is decreased to 0, the thyristor VT1 will be turned off. Okay? And in the negative half cycle, when the input voltage becomes negative, for the first part of time, I do not trigger VT2 yet. And therefore, starting from this point, until I trigger VT2, there will be no current flowing through the load. Therefore, load voltage will be 0. All this input voltage will be applied across this pair of thyristors. Load voltage will be 0. Until at this instant here, when I trigger VT2, VT2 will be conducting. Why? Because VT2 now, at this instant, will be under positive voltage, because at this instant, the lower side of input terminal will be having higher voltage than the upper side. So VT2 will be under positive voltage, therefore when you trigger VT2, the current will be conducting through the load VT2 and back to here. Okay? Therefore, load voltage will be same as input again. Okay? Because now this input is negative voltage, so the load voltage will also be negative. Until at this instant when this voltage is decreasing to 0, negative voltage decreasing to 0, and therefore the load current is also having the same waveform as voltage, and therefore also decreasing to 0 at this instant, and the VT2 will be turned off. Okay? So you can see very simple. And I'm also listing the waveform of the voltage across this pair of thyristors here. So when you turn on either VT1 or VT2, the voltage across the thyristors will always be 0. You see, this part and this part, these are always 0. But when those two are blocking, when these are under off state, then all the input voltage will be applied to this pair of thyristors. So you can see this voltage waveform of the voltage across the thyristors will be same as the input voltage. For this part, positive. For this part, negative. So very simple operation. Now let me ask the question. Why is it called AC voltage controller? will be changed. Okay? So his answer is that by changing this triggering delay angle, we are actually changing the load waveform, load voltage waveform. Okay? We can either, when alpha is 0, then we can have the load voltage will be the same as input voltage, therefore we have the full input voltage. When I'm increasing alpha, then the load voltage will be only having part of input voltage waveform. Okay? This could be a very big part or a very small part. Let's say if I'm triggering, I'm sending triggering delay angle signal here, over here, then UO will be having only a very small part of input voltage. Okay? So by changing triggering delay angle alpha, we are changing the output voltage magnitude. Somebody say this output voltage is no longer sine wave, right? This is so, it's just part of sine wave. Okay? So this is one of the disadvantages actually for AC voltage controller based on thyristors. But if you can always do Fourier series extension, you can always do Fourier analysis on that. Then you will always have fundamental component, right? For any periodic, let's see if this is the, okay, when you have only part of that sine wave, then your output voltage will be something like this. Okay. Somebody says this is no longer sine wave. This is no longer pure sine wave, of course. But if you do Fourier series extension, this can always be a, let's see, you always have a fundamental, let's say fundamental component, and then you have a lot of harmonics components. And actually the magnitude of this fundamental component will be changing when this triggering delay angle alpha is changing. Okay? So in this way, in this sense, we are calling this power converter as AC voltage controller. Okay? Of course, you can do detailed calculation based on this Fourier series analysis. Okay? You can calculate not just the fundamental component, you can also calculate the effective value of the output voltage, or RMS value of output voltage. Okay? You can also see that the RMS value of the output voltage is also changing with alpha. When alpha is changing, this RMS value is also changing, not just fundamental component. Okay? Therefore, you can do Fourier series analysis. You can calculate how much harmonics that will be appearing on the output voltage, and you can also calculate the power factor of the circuit. That means, if you still remember, power factor is defined as the ratio of active power over apparent power. And the active power is calculated in this way. Apparent power is input voltage RMS value multiplied by the current. So this power factor of this circuit can also be calculated. You can see that power factor is also changing with alpha. I will not get into those details. You figure out after the class why this is expressed in this way. I'm going to extend that into another type of load, inductive load. Inductive load means when you have both resistor and inductor in the load. And let's see what is the difference between this one and the previous one. Very naturally, you would be thinking there probably will be 2 points that this circuit operation is different from the previous one. One point is that when you turn on a thyristor, let's see over here, this is alpha. Why is this not labeling? This is the instant when you turn on the thyristors. Okay, this is alpha. You see that? This is the gate signal. UG1 is the gate signal for VT1, for thyristor VT1. UG2, this is the gate signal for thyristor VT2. So this leading edge over here is the time instant. Represent the time instant when you trigger VT1, and the leading edge of UG2 is represents the time instant when you trigger VT2. Okay. So the difference from this one and the previous one, between this one and the previous one, is that when you trigger VT1 for resistor loads, because load current is always having the same waveform as load voltage. Therefore, load current will be having the same waveform of load voltage, and therefore, because when you trigger VT1, load voltage will be having the same waveform of input voltage. So for resistor load, this current I/O at this instant will be increased from 0 suddenly to a certain value. But for inductive load, this will not happen. You always have an inductor here, therefore the load current will always not having this instant change because of that inductor. The load current will always be starting from gradually increasing from 0. So that's the first point. You can see here, load current will always be increasing from here gradually, from 0 gradually increasing load current. That's the first point of difference. And the second point is that you're probably also very familiar already with this kind of things. When this input voltage is decreased to 0 at this 0 crossing point, that means when VT1 is conducting, the load voltage will be the same as the input voltage. Therefore, on the load you are having the same voltage as the input. Therefore, the load voltage will also be decreasing to 0 at this point. For resistor load, that would be also the instant when the load current is also decreasing to 0. And therefore, at this instant, VT1 will be turned off. But because this is an inductive load, even when the load voltage, overall load voltage is decreased to 0, the load current is not 0 yet. You still have certain value of load current in the load. So this current will be maintaining the conductance of VT1. VT1 will still be conducting. Okay? Until when this current has finally decreased to 0. And at this instant, when this load current is decreased to 0, VT1 will be turned off. And therefore, load voltage after this instant equals to 0. Between this instant and the instant when the load current is decreased to 0, this VT1 is conducting. Between this instant and this instant, VT1 is conducting. Therefore, load voltage between these 2 points will be the same as input voltage. Okay? Those are the 2 points where this inductive load is different from the resistor load. Okay? And if you think about the physical process, actually, you can understand that when VT1 is conducting, and when this input voltage is positive, for this part, between this point and this point, this input voltage is positive, therefore UO is positive, therefore you are applying positive voltage across the load. So this side is positive, lower side negative. Therefore you can imagine that this inductor current, the load current, is actually increasing because you are applying positive voltage. Okay? And when this input voltage is negative, that means UO is also negative. That means lower side positive, upper side negative. You are actually applying negative voltage, for this part, negative voltage across the inductor. And therefore, the inductor current will be decreasing. Right? You still remember for inductor, you always have inductor voltage is always equal to L di dt. When this inductor voltage is positive, then your di dt will be positive. And therefore, load current, inductor current will be increasing. When inductor voltage is negative, di dt will be smaller than 0. Therefore, the inductor current will be decreasing. It's always like this. So the energy will be firstly stored in the inductor, and then when the voltage is getting negative, the energy will be released. Okay? So that's the physical process. Okay? So you can see this load voltage will be having this waveform, and until in the next half cycle, at this instant when I trigger, again at triggering delay angle alpha, when I trigger VT2, VT2 will be conducting because VT2 is under positive voltage, and therefore the current will be increasing in the reverse direction because now voltage is this side positive, this side negative. So the current will be increasing in this direction through VT2, reverse direction. Similar process as in the positive half cycle. Okay? And of course, I can do, again, detailed calculation, detailed analysis on that. Well, this time I can do, it's a little bit difficult than the resistor load case because now I have to list the differential equation here. When VT1 is conducting for this part between this instant and this instant when VT1 is turned off. During this part of time, I always have this differential equation. The voltage across the inductor plus the voltage across the resistor, this is the load voltage, will always be equal to the input voltage. And if the input voltage is sine wave, we always assume input voltage, AC voltage source is a sine wave voltage. Okay? Therefore, it will be having a representation like this. Okay? That is a differential equation. And then I have, this is the initial condition. Initial condition is at the instant omega t equals to alpha, at that instant, this current is 0. This current will always be increasing from 0. And therefore, you solve this differential equation, and that's the solution. You can find out the representation for the load current. Load current will be having this kind of waveform. increasing and then decreasing. And we have this exact representation for that load current. Okay? You can do this detailed analysis on that. And you can actually finally calculate when you consider at this instant, the I/O will be decreased to 0. Based on that condition, based on that ending condition, you can actually find out for how much time VT1 will be conducting. That means how long is this time interval counting from this instant to this instant. That's what we call conduction angle. Conduction angle. And we usually use theta to represent conduction angle. So you can figure out under different situation, let's see, under different situation how much this conduction angle is. And you can figure out that based on this equation, this conduction angle will be depending on alpha, the triggering delay angle. It will also be depending on another thing, phi. What is phi? Phi is actually the power factor angle of the load. Phi, power factor angle. Of the load. So this conduction angle, finally, you can figure out, will be dependent on two things: triggering delay angle and the power factor angle. Okay. So actually not so complicated. Let's do one step further. When you look at this load current waveform, you might be thinking, what happens if I have charged up this inductor to a very large value? Okay? You have already said that because this is a positive input voltage, therefore when VT1 is conducting, for most of the time you are charging up this inductor. So the inductor current will be increasing like this. And then when this input voltage is getting negative, this current will be decreasing. But what happens if when I want to trigger VT2 at this instant, if this current here conducting through VT1 has not decreased to 0 yet? Until this time, let's say if I trigger VT2 at this instant, if I trigger VT2 at a smaller alpha, that means when this current flowing through VT1 has not decreased to 0 yet, I trigger VT2. What happens? What? What's your answer?
This time VT2 doesn't conduct.
VT2 does not conduct. Okay? You can think about that during the break. What happens?